Welcome to the first video in our HEC-Commander Tools series. These are automation tools for HEC-RAS and HEC-HMS workflows that were authored with ChatGPT assistance. I'm Bill Katzenmeyer. I'm with CH Finstermaker & Associates. All of these tools were primarily authored by me for the Louisiana Watershed Initiative Region 4. So in this video, we're going to cover HMS-Commander, which is our HEC-HMS automation script. It was built specifically for our Louisiana Watershed Initiative Region 4 calibration workflows. It's built for unrouted HMS models. There's a lot of optimization and calibration algorithms within HMS for gauged flows, but we used HMS generally for our low detail areas that we didn't have gauged flows. So we provided unrouted models, which come with some difficulty with sub-basin parameter editing, scaling, etc. So instead of trying to use the internal tools in HMS, we built a script that would run everything and do it externally. So the basic steps of our workflows are sub-basin parameter editing, setting all of our deficit and constant scale factors, scaling our TC and R values, scaling our impervious grids above 1.0, which is something that needs to be done externally, as well as changing our recession baseflow factors. We've got some logic to handle DSS output file renaming, as well as providing all of our inputs as a CSV file for simplicity's sake, as well as reducing the number of user errors. There's also a version of the script that can do calibration regions by shapefile using GeoPandas. However, we're not going to cover that in today's video. So just a little bit of setup here. To be able to set up HMS-Commander, you need to install the Java Software Development Kit. This is an accompaniment to Jython, which is the Java Python interface that is used to run HEC-HMS. And so you need to download the Jython installer, install it to the default location. You also need to have the Java Software Development Kit, otherwise HMS won't run. And you also need to provide that specific version for whatever reason, the 20.0.1. As long as you have these prerequisites, everything else should be handled internally, and we're going to show that as in a demonstration here in a second. So it's a little 10x engineering in action. Let's get started. So I'm on my remote machine. I've got the HEC-Commander repository pulled up. HMS-Commander, you go to the HMS-Commander folder. We've got our with and without calibration regions Python notebooks. If you click on the Python notebook, you'll see it inside of GitHub, but to be able to download that, click on the three dots, click download. Simple as that. So we've got our copy already. So if you were to follow the quick start guide that's on the HEC-Commander website, I'll walk through that very quickly. If you go down to the bottom, there's a quick start guide. Get you to install Anaconda Navigator, install Visual Studio Code, install the Java Software Development Kit, Jython, as well as providing a window share for local execution. That'll be required for RAS-Commander. We'll cover that in another video. But for HMS-Commander, we do need to install Anaconda Navigator. We do need to install VS Code and put on the extension. So I'm not going to step through the installation of that, but I will start by just demonstrating that these scripts do work out of the box with a brand new environment. We create an environment for what? Our demo. We're going to create that now, and we'll move on to other things while that's creating. So just to explain very quickly, for our example today, we're going to use West Fork Calcasieu, which is one of our production models for Louisiana Watershed Initiative folder. This is our typical submittal folder. We've got all of our different types of data organized into classified folders, as well as our HMS model, our RAS 1D and 2D models. And if you can see here, I've already got some completed models to help me with our demo. Please remind me later. Within our HMS folder, it's a very straightforward HMS project. I've got it open in HEC-HMS already. We've got, again, unrouted HMS model, lots of sub-basins, no outlets, and no way to automate the analysis within HMS. And so within each one of these subbasins, we need to be able to vary the initial deficit grid ratio, maximum deficit grid ratio, constant rate, percolation rate, grid ratio, and impervious grid ratio. Also, if you change this impervious grid ratio above 1.0, and you also have any 100% impervious areas within your impervious grids, you'll quickly generate an error with HMS. And so with our script, it applies that scaling directly to the TIFF file outside of HMS, and then scales the input file, while also setting a limit of 100%. So it doesn't generate those invalid pixels. So it allows you to scale above 1.0 for impervious, which I think is useful, although we didn't use it heavily within our studies. We had more rural areas, so it wasn't as sensitive to that. We also need to be able to vary our time of concentration, storage coefficient, and our baseflow factors, initial discharge, recession factor, and ratio. Well, if you were attacking this without any automation, you would just, I joke, you click on the advanced user button, which is go to your project folder, and just go directly to your text input files. In this case, it's the basin file that holds all of these different inputs. So you'll see you've got a basin definition and then all of your subbasin definitions. Each one is pretty easy to pick out. Subbasin with subbasin name, all the different properties, and right in here you can see initial deficit, maximum deficit, percolation rate, impervious, time of concentration, storage, and then all the recession baseflow factors. So most of what we need to change is right here. So what our script does is it allows us to define those outside of HMS, define all the variations, and have the basin file changed dynamically, as well as the run file and the grid file if necessary for the impervious scaling. If we do provide a scaled impervious grid, we have to change the grid file to point to that other grid that we built. The run file is changed just to change the DSS file output. You can see here, this is from a previous run. It has the run 20 defined already, and that allows us to change the output file naming. And then other than that, the script really just runs HMS automatically for each one of those CSV inputs. So let's get right into the script itself. I'm going to close out HMS. We don't need it anymore. The HMS model runs. It's got a run file set up. I didn't cover that. But if you were to click compute, I think any of these automation scripts, they don't work unless your model works. So if you click run and you get errors, you're not going to have any luck trying to automate it. It's not going to take away that hard part of the work. So let's open up HMS-Commander. This has already been populated. I downloaded the without calibration regions version of the script, and we are now populating it. So first thing to do when you first download these scripts, I don't have the option, unfortunately, of collapsing all these code cells off the bat. These are code forward notebooks, and what I mean by that is there are no, other than using publicly available libraries, there's no specialty code that's hidden away in a library. Everything's in this notebook. It does create a large notebook, but it does allow all of the logic that is, essential for manipulating the HEC-RAS files and everything else is within this notebook and can be changed. So to the extent that, AI can be used to directly edit the functionality of these notebooks, that's optimal. You don't have to download multiple files, or I don't have to build Python libraries to then publish and then worry about backwards compatibility. We're not at that level with these scripts. I barely could code last April, and I think one of the fun things about this exercise is to show how AI can be used to build functional, useful scripts of small to medium complexity without needing to necessarily adhere to all of that. Although it does become useful as you create production software. I do expect whatever of value that's within these scripts will eventually get pulled out into libraries and into a more extensible and standardized class library, etc. So just to start off, for every one of these code cells, we provide a description at the top that describes the contents of the code cell. That allows you to just collapse these code cells, and then you'll just have a list of code cells. You generally don't need to look at most of these. You just need to worry about the inputs if you're just using it for its intended purpose, without having to sort of edit or do anything different. You just come down to the left, and here I'm just going to click all the way down. So that collapses the notebook into something more manageable. Now we can focus just only on what we need to actually look at. So to start off, we have these user inputs. To the extent that we could, everything is determined automatically from the least number of inputs required from the user. Try not to overcomplicate the inputs, because every one of these inputs, you have to then explain the logic of how they're used, or have it be intuitive. And frankly, most of these text-based interfaces are not just intuitive to people, so it's much easier to try to just simplify the operation as much as possible. So here we only have inputs of the actual HMS project directory and the basin file, as well as the run names. And the run names are provided as a list. And that's because you can run multiple run names with the same CSV file input. There's also our CSV input, which we should go over now. I provide an example of the CSV input. There's also lots of documentation on the HEC-Commander website, or HEC-Commander Tools GitHub. We can go through this very quickly. Now, just to make note, there is a slight difference in how these are described in the GUI of HMS versus the actual basin file, because I expected this to be an automation of, something that somebody would probably do within the basin file, probably manual copy replace all, find replace all would be probably the way we would have to do this without these automation tools. That I wanted to follow what was in the basin file. So each one of these inputs, except for user run from CSV, is based on the nomenclature of these this basin file. So you got the initial deficit scale, maximum deficit scale, percolation rate scale, impervious area scale, recession factor, initial flow area ratio, threshold to peak, time of concentration, storage coefficient, and that's it. So for each one of your runs, you define each one of these factors. And that allows you to build runs up to 100 runs. And you could do more, frankly, but up to 100 runs is kind of logical. That's what RAS will let you do at a time for an input. So keeping things within 100 run sets are pretty reasonable. And you're able to then vary. Here we've got, we vary our initial deficit from 0.7 to 1.15, just looking at the sensitivity of that figure, while also looking at two different percolation rates. So that's just our test case. We're going to save that. Well, not save it. It was fine before. And close out this basin file. And so this script will create the same value. It will overwrite the same value for all of your subbasins. If you're looking to change the spatial variation of what you put into those subbasins, you have to create calibration regions. And there's another version of the script that allows you to create, under each run, you're able to then define for each calibration region and each run what those values should be. And it allows a spatial relate back to your subbasins. But we're not covering that here. Hopefully, if you got good gridded data sets, you're not having to do all that. Let's finish going over all these inputs. You do need to provide the full path of that CSV that you're providing as your input. It's going to read those columns directly, so as long as you don't change those column names and you provide valid inputs, there should be no issue with these CSV files. For the HMS run names, you're able to provide multiple runs. So if there's multiple events, or say you want to do an AEP event set, you want to do 5, 10, 25, 50, etc., you can put those HMS run names right in here, as well as varying those factors. You also have an HMS DSS suffix. Now, this is put here because you don't want to have, if you have a similar run set and it's called run 1, run 2, that's all the script is going to do automatically. It's going to number the runs according to your CSV file. But these suffixes allow you to then to label different run sets separately. So here I've put in today's date, and this is just going to tag this on to the end of every single one of your DSS file names so that you're able to differentiate them. There's also a quick override here that allows you to turn on and off the override of no base flow to recession base flow. If you don't have a base flow set and you do need to set it for some reason, for us, we need it for our RAS models. So in some cases we didn't have it. So we just have it override to set that as true. You can set it as false if you have no base flow, or if you have another base flow factor, you just won't have the ability to change those factors within the CSVs, but it will ignore the inputs in the CSV file and not do anything with them if this is set to false and those factors are not present in your basin file. So for additional settings, you do have to provide the executable path for HEC-HMS. Here we're using 411. You do have to provide some paths where it's going to write a Python file as well as a batch file to actually run HMS using Jython. I've had that set to the default Jython folder. If for some reason you can't install at the default Jython folder on your C drive, you don't have access to the C drive for some reason, then you will need to change that to wherever you installed Jython or somewhere within your user folders. It doesn't matter as long as you have write access to that location. These are just temporary files that need to be written so that they can be run to affect the actual automation portion. There's also heap sizes for your Jython instance. By default, Jython only includes 1 GB of memory for each instance, and you need to override that if you want to run larger models. The way you'll know you need this is if something, say, runs just fine in HMS under normal circumstances within the GUI, but then you try to run it through HMS-Commander, and you find that it just stays at 100% CPU and never finishes, and it's also a model of significant size, it's probably because of the memory settings. Jython enforces, because it's wrapping your Java instance in an environment, because it allows you to then define something that's less than the default, you may run into the cap. So the way to try to avoid that is just to increase your heap size. This is all command line parameters that are passed through those Python and batch files. So we simplified it by just allowing a simple user input. There's also, this is a deprecated bit of logic that's going to eventually come out of these scripts, but in 4.9 and earlier, you would get an error if you didn't have a canopy method set, and so we would just set to simple canopy method with 0, just to avoid the error and push past the calculation and make the model run a little faster. But we don't need that anymore. I'll set it to no. That logic will be removed at some point. So let's continue. We're going to explain the operation of the script before we go run it. The very first thing that's going to happen is it's going to install and import all the required Python packages. Let's just go ahead and demonstrate this because it's only the first few code cells. I'm going to select my kernel that I just made. Should have. Just made one. So let's reopen VS Code. See, again, it's going to do this. There's our new environment. We're just going to come right down here and run the first couple of code cells. So when it gets here, you see it's working away. It's installing all those packages. I'll show you what it's installing. Oh, there we go. Installing pandas. Subprocess is already part of default Python installation. So itertools, GeoPandas, Shapely. I don't think GeoPandas is required, but we just include the same little code cell. So here we go. We're done. That's the automatic environment setup that's necessary for these. So yeah, that prevents us from having to get the users to go run things in the terminal, debug. We try to use the publicly available packages that are reliable with installation. The only ones that are less reliable, perhaps some of the DSS tools. But for this, it's pretty straightforward. It's going to check for Jython. If Jython doesn't exist, it's going to give you an error. But here, it can tell that Jython does exist, so it continues on. And then our next step is going to be to build that batch file and Python file. So it's going to run through that, write those files out to get everything ready to automate. So then here it's going to determine the project name real quick. It's a simple bit of logic. Then it's going to calculate and print the necessary file paths. So these are all the file paths that it needs to complete its work. Then we're going to create a lock file and logic for working file backup and restore. So one thing that's important to note inside of your HMS folder, and it just created those back files, because you're going to change potentially your grid, run, as well as your basin file, it's going to create a lock file as well as backup files of all those, because your TCNR is in your basin file. It's not stored anywhere else. So if you don't restore that after scaling it, then it gets iteratively scaled. So we do have some file backup and restore logic. If the lock file exists, then it will restore from the back files until a run is completed. So if for whatever reason, say you are, your run fails, you restart the script, and you're having frustrations because you feel like you just changed something and it got overwritten. You might have changed it in your basin file, but your lock file and your back file is still there. And so until you come in here and either manually restore these or delete the files, knowing that you, say, didn't scale TCNR and you're not too worried about the run file and the other linear scaling factors being changed, then you can just delete these files and it'll continue on. But if you do, say, while these files are all present, if I were to restart this script, move on, come back tomorrow, make a change in the basin file, the first time I run this script, it's going to see the lock file. It's going to restore it from backup. It's going to think, well, I made changes and did these backups, and obviously I didn't finish. So I need to restore these from backup to restore them to the original condition. Otherwise, we could end up in a race condition where the basin file, the TCNR, just get iteratively changed, and eventually that information is lost. So that helps us with that logic, but it could prevent a user from using this effectively. So I want to make sure to walk everybody through and understand what the logic is of these scripts. Then it's going to read the CSV file. So here you go, all the inputs straight into the script, and we've got all of our functions. And just to explain what's going to happen, Jython allows HMS to run headlessly. So we're not going to see anything happen, but we are going to see the script, or the files dance, essentially. So let me move this over a little bit so we can see it. And as I define the scripts, now run the main logic, what happens here, the basin file gets written, all the other stuff gets written, but before anything starts, before the script continues with any single run, it's going to look for the output file. So let me get this back up here. Processing run number 1. The output DSS file does not exist for preparing HMS run. So it's really important to understand we didn't want to put a complicated execution logic. I didn't want the user under, say, a normal scenario to have to say which runs they wanted to run. So what the script does is it looks for the DSS file output. And that's why you have a suffix. If you are adequately changing the suffix every time that you do a new batch, then it'll always run all. But if you're trying to go back and say fill in runs on a batch, something failed, say your maximum deficit was, scaling factor was too low, and the maximum deficit was less than the initial deficit, and so it gave an error. Typical way of giving an input that just gives nothing as an output. And so you want to change that to some other value and rerun it, but you've got 100 laid out, you've already run, you're only changing 2, and you want to be able to go run just that one. Well, without us going in and being able to specify that with some sort of logic or input, it's very difficult to do effectively. But by having it look for the DSS file output, you just delete the DSS file and rerun the script, and just understand that logic's there. So if you rerun the script you've got a bunch of output files, it's not going to overwrite those output files. You do need to, every once in a while, look at your output files, make sure that they are not zero, size. So here we've got 92 megabytes on our first DSS. These are ghost DSS files. Don't ask me why HMS creates these, but it does. For other events, it creates the DSS file outputs even when it's running just one. So here you can see it's running demo 1. Now we're on, run 1 of the demo for today. We're on run 2 of the demo for today. So let's jump right in here real quick. We're on run 2. Got a first sub-basin, 1.1, 1.0, 0.5, 1.0. This doesn't change. So we've got our time of concentration, storage coefficient did not get scaled on this example. 0.1, 1.0, 0.1. They're a little out of order. You can rearrange these in the CSV. It makes no difference what order you put them in. But we added these at the end because that was the last feature to get implemented into the script. So either way, that's it. So you can see what it's doing. It's just running for each one, already moving on to run 3. And so with this, we're able to create run sets out of HMS for a range of different calibration factors. This is fairly simple to change. I mean, if you were to come in here and look at all the different functions, it's fairly straightforward to try to, say, rename some of these columns, and instead of doing deficit and constant method, we could use any of the other methods. It's fairly straightforward once you have most of the hard stuff in place, which is the Jython files, a notebook already set up with all the inputs, a workflow, and functions in place that really only would need to be changed or edited. So it's really fun coming up with this. I think it's a really great example of using AI to come up with functional scripts quickly. I think there's a lot of value here for other people that could grab onto this, edit it for their own use, as well as the primary is just within the Louisiana Watershed Initiative. We're all using deficit and constant. If you're not using recession baseflow, you're using none, or using linear baseflow, but those factors aren't super sensitive. They're not changing a lot. So the main things that really would need to change we're covering. And so for the people who do have unrouted models like us, hopefully this provides some respite for changing all these basin files. Even in our consequence modeling, we'll be doing the same thing with a lot of our storm transposition. We'll be feeding in DSS files and providing automated runs for outputs. And so with that, we're going to let these finish. One thing to be aware of when this does finish, it will restore the HMS folder and all the files back to the condition of whatever it was before the back files were made. And so the intention here is I could actually download from a repository, from a website, these models, download them, unzip the folder, and run a whole set of runs, and then end up with but still have a resulting model that didn't change. That the only thing that changed was temporally long enough to get all of our calibration runs out and verify them. And then when you go back, you can, once you find the one that works the best, you can, of course, change those parameters manually, but to basically not permanently alter the model unintentionally by using this. Because we are changing, say, we're not creating a new run. We're not creating 99 runs for each, whatever. It's changing things dynamically and then changing it for the next and the next and the next and the next. And so you don't want to then take that. You don't want to take that theory of operation and then leave at the end with the last run still in there. You want it to be to come in, make the changes, and then restore everything back to the way it was before exiting. So That's what the intention of this is, other than the output files. And so, as you see here, we're already on run 4. We'll let this finish and we'll come back in for the next video, which will be HEC-Commander, using these output files to run our 1D models, run as 1D inputs on our 1D models. So stay tuned.